Okay, so it's just a little demonstration on how to do free body diagrams. So on the worksheet on the left hand side, you've got a couple of different situations, and I just want to go through some sample problems for you to try to explain how to do them properly, especially for anyone who missed out on lessons this week. So what we want to be able to do is represent the forces acting on each object using a free body diagram. So a free body diagram separates basically takes everything else away except for the forces. That's it. We take all the forces that are acting on that one object and we usually put them pointing away from that object. Okay. So for the first one, we've got a guy standing still. Okay, so he's standing and I am going to represent him using a free body diagram. So I'm going to draw a box, but some people draw a circle. Doesn't really make a difference. Some people like to draw a circle, I like to draw a box, doesn't really matter. We show the two forces that are acting on him. Right now he's got a force of gravity that's acting downwards, known as his weight. So another way to do this, I've drawn it here in green, but I guess I could do it again, and I could represent him like this, and I might call this the force of gravity, F subscript G. And then pointing upwards, I would have the normal reaction force. So again, just have a look back on the list of forces that we looked at in class. So the normal reaction force might sometimes be called Fn. I will often call it Fn, or maybe people would just call it uppercase N for the normal reaction force. Okay, so that's him. Done. Next one, we've got a car, and let's assume that this car is accelerating to the right. So it's not going at a constant speed, it is accelerating. So again, I've got a complicated looking drawing over here. We simplify that into something super simple. Take away everything else, because if you notice in this picture, we've got it actually is a little bit more complicated than I pretend it to be, because it's not just a car with wheels, it's also the ground as well. Okay, so we're going to take all of that away and we replace it with just one object. Now again, you can use box, you can use circle, doesn't really make a difference. So I'll start off. I think it's always a good idea maybe to start off with the obvious forces. I would have the object's weight acting down. There's the car's weight. Of course, the car is not falling towards the center of the earth, so therefore there must be some normal reaction force, or force normal to the surface, that's pushing it up, and that's pointing this way. And of course, that's the contact force. I'm going to call it N, uppercase N, for the force normal. This arrow should be the same size as this arrow here. Okay, so so that means that in the up-down direction, if you like, the forces are balanced. All right, so just like we saw in the last case, we had balanced forces because the arrows were the same size. Okay, so then we have a look and you say, well, it's accelerating to the right, so there must be some force that's being applied to it to the right. So I'm just going to label it as a force applied. You could very easily call it the force of the engine. You could call it thrust force, something like that. I'm just going to call it force applied. And then there's more than likely one or two forces that are slowing it down. I'll put one here, make it fairly small. This one might be something like the force of friction. And let's say it's probably not going very fast. So I've got force of air resistance there as well. Okay, so to see whether or not these forces are balanced, we look to see whether or not it's accelerating. Okay, so we ask ourselves, is this thing accelerating or is it not accelerating? If it's accelerating, the forces are unbalanced. Okay, so this thing is obviously speeding up and it's going to the right, so that means the forces are unbalanced. So if you were to sum up all the forces, you would see that in the up-down direction, those forces cancel each other out. Okay, But then in the right, left, or the x, the positive direction, the x direction, we would have force applied, and this one is obviously greater. Force applied is greater than the sum of the force of friction and the force of air resistance. Okay, because it's accelerating to the right, which means it's going to start to speed up. Okay, so give those examples a shot, and don't forget to do your Newton's second law worksheet problems there as well. Okay, thank you.